Yeah, this electronegativity has a key role in this chemistry. So electronegativity is defined like this: the ability of an atom in a molecule to attract electron to itself is called the electronegativity. It is something like this. Say, if you have a bond between hydrogen and hydrogen, these two are identical atoms, and the electron pair of this bond will be exactly at the midpoint. Why? These electrons are negatively charged, and the nuclei positive. Positive nucleus of hydrogen, another positive nucleus of hydrogen, and we have two electrons at the in between these two positive nuclei. This is positive, electrons are negative. Therefore, what happens? This pair of electron will be attracted by this positively charged nucleus of hydrogen and also by this nucleus. But both of these hydrogen atoms these are identical atoms. Their abilities, their attractive powers are same. Because of the same attractive powers, the electron will be exactly at the midpoint. But if this hydrogen atom, the charge is +1, is bonded with another atom, say fluorine, hydrogen here, fluorine here. Then the fluorine nucleus has 9 pluses. The charge is now 9 plus. The nucleus is positively charged. It has 9 protons. Therefore, the charge is 9 pluses. Still, we have a pair of electrons in between these two atoms. Then that electron may be much closer to the fluorine. That will be much closer to the fluorine. Why? This 9 charges +9 will attract electron much strongly than they attracted by this hydrogen nucleus. Therefore, the bond electron will be much closer to this hydrogen. Now, the relative ability to attract bond electron is higher in the case of fluorine than hydrogen. So we say the ability of an atom in a molecule to attract electrons to itself is called electronegativity. So when we compare the electronegativities of this hydrogen and fluorine, fluorine has a higher electronegativity. Then what will happen if hydrogen and chlorine bonded together like this? Obviously, this chlorine will attract the electron towards that. Why and how? We have hydrogen with only one charge, one positive charge, 1 plus. But chlorine, it is 17 pluses. It has 17 pluses. Why 17? The atomic number of this chlorine is 17. That means chlorine has 17 protons in its nucleus. Then, when we get this fluorine and chlorine, it is obvious that the electronegativity of chlorine must be greater than the electronegativity of fluorine. But if you really go through the real electronegativity values, electronegativity has a value. But when we compare those values, you will see that the value of fluorine is 4.0 and chlorine is 3.0. That means fluorine has a higher electronegativity than chlorine. That means the nuclear charge is not the only factor which decides the electronegativity. Then what else? What are the other factors? So mainly the electronegativity, there are many factors affecting on that, but mainly the electronegativity depending on two factors. First one is the nuclear charge. Nuclear charge. The second one is the size of the atom. Size of the atom. Then, when the nuclear charge is getting higher, the electronegativity also increases. But when the size is increasing, what will happen? See, if you have hydrogen and fluorine, fluorine is a smaller atom than hydrogen and chlorine. Chlorine is a bigger atom. Therefore, the bond length is high in the case of HCl than HF. Therefore, the attractive power of electron by this chlorine nucleus is relatively lower compared to that of fluorine. Therefore, the chlorine has, although this chlorine has a higher nuclear charge, it has a lower electronegativity. And you know that even in your O level, the atomic sizes decreasing from left to right across a given period. See the sizes, if you get that the sodium here, sodium, oh, I get that the lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. Atomic sizes are decreasing. See, it is decreasing. All these outer electrons are added to the same main energy level. So nuclear charge is increasing, at the same time the electron charge also increasing. Why? When we move from one electron element to another element, by arranging all of them in the increase in order of their atomic number, the nuclear charge is increasing and also electron will be increasing. That means, say, you have here the nuclear charge is +3 in the case of lithium, beryllium +4, boron +5, carbon +6, and so on. Then the number of electrons on the outermost shell, the outermost number of electrons on the outermost shell will be like this. Now you know how to write down the electron configuration. Then this will be written as 1 is 2, 2 is 1. Here 1 is 2, 2 is 2. Here 1 is 2, 2 is 2 and 2p1. That means there are 3 electrons on the outermost shell. You have 3 electrons on the outermost shell and 5 charges here. Then the attractive power will be high in the case of boron than in lithium. So the size is decreasing. Why? The electron cloud is now attracted by 5 positive charges. So it is increasing. And remember that, Puta, later you will study under your physics. something like this. Say you have two charges. Maybe here plus and here minus. Say this is Q1 charge and here Q2 charge. Then these are opposite charges. There will be a mutual attraction. F and F. Mutual, equal on each. That can be calculated by F equals K times Q1, Q2 over R square. R is the separation between, the distance between these two charges. Then when Q is increasing, when the Q value is getting bigger and bigger, the F value will be increased, therefore the R value will be decreased. That's why the size of the atom decrease from left to right. You may have already studied that thoroughly under the first lesson. All these are known things now. If you have done the variation of the atomic radii in that part. If the charges are same, then there will be a repulsion. Again, it is mutual. Repulsion, F. That F also can be calculated in the same way. But this is a repulsion. Earlier it was, if the charges are opposite, then attraction, otherwise it is repulsion. Maybe plus plus or minus minus. Therefore, that's why, because the charges are increasing, Q1 and Q2, say Q1 is the plus charge, say plus 5 in the case of this boron, plus 5, the negative charge is minus 5. Now, if you just consider the outermost shell, it has only 3 electrons, then it is minus 3. Then this will be minus 15. Minus sign indicates that it is attractive. That means opposite charges are available. If you get this on carbon, the nuclear charge is plus 6 and in the outermost shell you will have only 4 electrons. So it will be minus 24. Here 15, now 24. So because of the attraction, power is increasing, the size will decrease. So when the size is decreasing, what happens? The distance between the electron, outermost electron and the nucleus will be decreased. So the attraction power will increase. Therefore, when we move from left to right across a given period, the electronegativity is decreasing. The electronegativity values of this lithium to right 0.9. This is, you need to remember these values and these are very easy to remember. Just look at this. This is 0.9, this is 1.2, 1.5, 1.8. No, I'm sorry. That is starting from sodium. This is 1.0, 1.5, 2.0, 2.5, 3.0, 3.5, 4.0, and electronegativity is not defined for neon. Why? The electronegativity, see, it is easy to remember. Starting from lithium, it is 1, it is increasing 0.5 wise, 0.5, 0.5, 0.5, then up to fluorine. Remember that fluorine has the highest electronegativity among all the electron elements in the periodic table. If you get all the elements in periodic table, this fluorine has the highest electronegativity. That means it can attract electron much strongly than any other element. So the electronegativity is the ability of an atom in a molecule to attract electrons to itself is called that electronegativity. The smaller atom tends to have higher electronegativity because the distance between their nuclei and the electron cloud is short, enabling a stronger pull on electrons. Electron will be pulled towards the nucleus strongly when the charge is increasing and also the size is decreasing. The size is decreasing from left to right. At the same time, the nuclear charge will also decrease. Nuclear charge is increasing, therefore the electronegativity will increase from left to right across a given period. Then trends of this electronegativity across a period. Period means we have our periodic table. These are called the periods. That means we have, if I just get the 20 elements periodic table, you have already studied under your O level. And if you have finished that, then you know definitely uh, everything about the periodic table, how it has been constructed, and what is the periodic law, and everything is known like this. Say like this. Then these are called the periods, and these are called the groups. Group numbers are 1, 2, then 3, 4, 5, 6 up to 12 D block elements. Again, after that, we have the P block elements. Group number 13, 14, 15, 16, 17, 18. 18 will not form compounds. That's why we are called the noble gases. Right. So, across the period means from left to right. From left to right, like this. See, group number 1, 2, 13, 14, 15, 16, 17, 18. Here I am not going to go in detail about the group numbers. We will discuss in detail under the first lesson. We have separate lesson for the periodic table. Then electronegativity increases as we move from left to right across the period. This is due to decrease in atomic radius, which brings the outer electrons closer to the nucleus, enhancing the atom's ability to attract electrons. Because of the decreasing of the size and the increase in the nuclear charge will increase the electronegativity from left to right across a given period. Here we are considering only the S and P, but here I have given you the electronegativity table, the Pauling table, and also another table. Okay, we will discuss those in detail later. Then from left to right across a given period, the electronegativity is increasing due to the increasing of the nuclear charge and the decreasing of the size. So write down these elements, electronegativities, electronegativity. We just put that En to denote that electronegativities. And here we don't define the electronegativities for the group number 18 elements. All that noble gases. Next one, down group. Down group means if we have 18 groups in our periodic table. The group number 1 we have lithium, sodium, potassium, rubidium, and cesium. Group number 2 we have the beryllium, magnesium, calcium, strontium, and barium. Group number 13 we have boron, aluminium, gallium, indium, and thallium, and so on. Then what happens when we write? Then what happens? See, if you just get the lithium, sodium, potassium, rubidium, cesium, the atomic numbers, what happened to the atomic numbers? Here, the lithium atomic number is 3, sodium atomic number is 11, potassium 19, and so on. Atomic number is increasing down the group. Then what should happen? The electronegativity has to be increased down the group. But I told you that the electronegativity depends on two factors. One is the nuclear charge, and the other one is the size. But when we move from top to bottom, size is increasing much faster than the atomic number. The effect of the size will be prominent. Therefore, the electronegativity is decreasing down the group. If we just get that the um, elements and electronegativities, negativities, elements say lithium, sodium, potassium, rubidium, and cesium. The electronegativity values: lithium 1.0, sodium 0.9, potassium 0.8, rubidium 0.8, and cesium 0.7. Here, the down the group. This is the way that moving down the group. Lithium, sodium, like this down the group. It is decreasing because of the increasing of the Ryle size faster than the increasing of the atomic charge, nuclear charge. So down the group, what happens? The electronegativity decreases as we move down a group in the periodic table. As the atomic size increases, the nucleus pull the bonding electron weaken and the lead into the lower electronegativity. So now we know the variation of the electronegativities across the period. It is increasing. Down the group, it is decreasing. That is the general rule. But remember that in science, or especially in chemistry, we can't give some general rules. Right? Normally, we have exceptions. because the not science is not happening according to our rules, but we are setting rules by studying the nature. Science is studying the nature, and we formulate some what is called that the formulas to explain the mathematical, or sometimes we construct some logics to explain them. Sometimes when we are failing to explain those things, we say exceptions, because by applying all the known theories and all the known mathematics, sometimes we can't give a general rule for the behaviors of natural things. So we say exceptions. In the case of this chemistry especially, there are plenty of exceptions, though we say or state some rules. This is something. Why? We say the electronegativity is increasing from left to right across a given period and decreasing from top to bottom in a given group. See, noble elements means the elements found in the group number 18. Earlier you said that in O-level group number 8, neon, argon, krypton, xenon, and radon. Now we call them as the group number 18 elements or noble gases. In the case of noble elements, we say that the electronegativity is zero. Why? They don't form. Actually, we don't say that it is zero. It is very small, non-zero. There may be a value very small, nearly zero. Sometimes we say zero, but it says that in many books they say it is non-zero, but very small. But if you get the fluorine, the most electronegative element is fluorine, and fluorine has an assigned electronegativity value that 4. Its smallest atomic size allows is to exert a strong pull on shared electrons. Remember that in our periodic table or among the elements in the periodic table, this fluorine has the highest electronegativity. That is the cumulative effect, or we call that the resultant effect of the nuclear charge and the size. You can't just explain by using the size or the charge. You have to get the resultant effect. If we have done the thing called that the resolution of these forces, say you have a force on a point exerting like this, say this is F1 and this is F2, then the resultant force will be in between these two, and if the angle is alpha, then this resultant can be calculated R square equal F1 square plus F2 square plus 2F1 F2 cos alpha. Right? That means this is the resultant. I think you have already studied about these things in physics. So right. So in the same way, here we have to consider the effects of both of them. Here I just used, there is no relationship between this equation and the uh, electronegativity. I just explained that when we have different factors affecting on something, then we have some rules to explain them. In the case of electronegativities, we are not going to explain the theories behind that, from where this electronegativity term came and what does really do, but we just get the effect of that. Electronegativity is the attractive power of, say, just the attraction of the bond electron towards the nucleus. So fluorine has the highest electronegativity value, and it is 4. The Linus Pauling is the first scientist. See, the Linus Carl Pauling is the one who said this scale. Still, the Pauling scale is the widely used in electronegativity scale. That is not the precise one, but anyway, uh, we are using that as our basic electronegativity table. And the other thing is the cesium has the lowest electronegativity. Cesium has the lowest electronegativity because that cesium is the biggest. Because that cesium is the biggest atom, so it has the smallest electronegativity value, and it is set to 0.7. It has been set to that 0.7. See, as one of the least electronegative element, the cesium has a value of 0.7 due to its large atomic radius and weaker nuclear attraction of electrons. The Linus Pauling electronegativity scale. This is the very first electronegativity scale and also widely used in scale. See, the American chemist Linus Carl Pauling in 1909 to 1994, that was his period, they introduced the first and the most widely used electronegativity scale known as the Pauling scale. In general, the electronegativity increases across the period from left to right in the periodic table. However, as atomic number increases within a group, the electronegativity usually decreases, though there are exceptions. I told you there may be some exceptions, particularly among the transition metals. Transition metals, uh, transition metal has a different meaning, but for the time being, you can get it as the D block elements. I hope that you know all the blocks in our periodic table, like S block, P block, D block, F block. Yeah, I'm not going to go in detail about that because that is not related to this lesson. No need to know about that. See, for transition elements, we simply call that the D block element. There is no consistent pattern in the electronegativity due to the variation in the atomic radii and the stability of the electron configurations. This irregularity makes predicting the electronegative trends in the transition metal more complex. We cannot set general rule for the variation of the electronegativities in the D block. See, this is the Pauling scale. Pauling scale in electronegativity. The most electronegative element is this fluorine, and it is 4. And the least one is we call the cesium, not the francium. Why? This francium is radioactive. Radium is radioactive. And remember that bismuth, the atomic number 83. Bismuth. Bismuth is the highest atomic number. Bismuth is the element with the highest atomic number, which has at least one stable or one non-radioactive isotope. After that, if you get any element, all the elements are radioactive. All the elements are radioactive, therefore, we will not find stable atoms or isotopes. That's why we don't get this francium and radium in our studies in periodic table. We don't get it because mm, they are changing. In course of time, they are changing. So, lithium, sodium, potassium, rubidium, cesium, the electronegativity is decreasing. Beryllium, magnesium, calcium, strontium, and barium, again, it is decreasing. There may be some equal values. We will discuss about them later. See here, the calcium and strontium, those are same. Rubidium and right. So down the group, the electronegativity, what happens to that electronegativity? You can see that it is decreasing. See, lithium, sodium, potassium, lithium, sodium, potassium, rubidium, cesium, like that is decreasing. And across the period, you can see that if you just get the short period, these are called the short periods. Lithium, beryllium, boron, carbon, nitrogen, after fluorine, it is gradually increasing by 0.5. But in the third period, starting from the sodium to chlorine, you can see that it is increasing 0.333 up to phosphorus only. Sodium, magnesium, 0.9, 1.2, aluminium 1.5, sodium 1.8, phosphorus 2.1. But after that, there is a different in that increment. What is that? From phosphorus to sulfur, it is increasing by 0.4, and from sulfur to chlorine 0.5. But anyhow, you can remember that up to phosphorus, it is increasing by 0.3, and then 0.4 and 0.5. But just look at this. These elements are known as the D block elements.